Good afternoon. My name is Olga Savchuk, and I'm with INPLUS Center for Innovation, Technology and Policy Research at Instituto Superior Técnico in Portugal. Today, I will talk about user-centered design and evaluation of decentralized energy systems. By the end of this presentation, you will know how to implement an approach that overcomes social resistance to new energy projects. I will begin by thanking my colleague Andries de Vries for collaboration on the survey, Professor Henny van der Wind for advice and inspiration, Team VGL Company for hosting the study, and Erasmus Mundus for financial support. Today we will explore the need for decentralized energy solutions, get to know participatory approach to community energy design, and focus on application to a Dutch neighborhood. Energy security, climate change, and resource scarcity motivate societies around the globe to install more renewable energy. However, as the renewable energy production grows, the energy system experiences several grid challenges. This could be addressed in two different ways. Centralized solutions require system-wide changes, which result in large investments and long-term planning commitments. Such decisions can lock the country in a specific pathway. In contrast, decentralized energy solutions can be better tuned to the local needs and available resources. The risks are diluted, and the new energy systems can serve as testing grounds for technological alternatives. Additionally, such projects increase the local energy awareness. Technical robustness and social resistance are two major concerns when it comes to decentralized solutions. Lack of social acceptance has impeded numerous energy projects in the past. To address these challenges, our study proposes a holistic approach to design, evaluate, and select a technically robust and socially sound decentralized system. The Netherlands have a long-standing interest in sustainable energy transition, and particularly in decentralized solutions. As of 2019, there are 85,000 residents that are already participating in local energy communities. That is why we applied our approach to a Dutch neighborhood. Participatory approach to community energy design, or PACE, is based on the participatory integrated assessment used in the water management field. We modified and adapted it specifically for energy applications. PACE begins with a situation analysis. This includes extracting user preferences and technical constraints. For user preferences, we conducted a survey among Dutch users to better understand their energy needs and priorities. We also verified the results against published studies. We learned, for example, that nearly 40% of the residents believe that locally produced and consumed energy is the most important aspect of the new system. We distilled the survey results into specific criteria that you can see on the right. For technical constraints, we analyzed the Dutch context. The country has a well-developed gas infrastructure and experience in wind energy. Also, Dutch society has a strong environmental commitment and expects a high comfort level. Existing housing stock affects energy demand and the availability of space for new installations. Demographic features define demand profiles and potential flexibility. We identified a number of technical constraints based on the context analysis. For instance, the housing stock and shading define the rooftop area available for solar power. The second part of PACE is system design, which is an iterative process of design optimization and user feedback to obtain a set of final systems. To begin, we described a reference case where insulation varies across houses, there is some PV installed, and users are supplied by centralized grids. The NVGL team designed 4 alternative systems. Each emphasizes different user preferences from the survey. Biogas power system prioritizes energy autonomy and low environmental impact. It includes better housing insulation, a shared biogas digester, individual energy converters, and intra-week gas and battery storage. All-electric system prioritizes high comfort and energy neutrality. It includes extra rooftop PV, interconnection among houses, individual converters, and intra-week batteries that are individually installed. Smart grid system focuses on low costs and low environmental impact. It includes improved insulation, smart devices, interconnected houses, large wind turbine, communal converters, and shared intra-week battery. Finally, power-to-gas system emphasizes high comfort and low environmental impact. The system includes extra rooftop PV, a large wind turbine, interconnected houses, communal converters, and shared intra-week battery. For each system, we modeled energy flows over a year under typical and extreme weather conditions. For this, we applied established energy models developed by the NVGL company. Here you can see an example of heat, electricity, and gas demands for a winter week in a representative detached house. Using these demand patterns, we optimized energy flows by pricing emissions and minimizing overall costs. Each system was initially sized at the maximum possible capacity of every device. They were required to always meet energy demand, even during extreme conditions. The motor model then optimized the use of converters and storages. Based on optimized energy flows, we sized installed capacities by adding a safety margin of 20% to peak asset use. The resulting designs and their costs are presented to the users for feedback. For example, they may set an upper limit to acceptable cost, which could eliminate some designs. In our pilot study, the financial support came from the industrial partners, hence all systems were considered. At the last part of BASED, we assess, rank, and select the final systems according to the user preferences. In our case, energy autonomy, resiliency, cost, environmental impact, and user satisfaction. The reference case is used as a standard to measure energy autonomy, or how much a system relies on the grid during a typical year. The electric and power-to-gas systems rely on the grid to bridge the time gap between supply and demand. They may be energy neutral, as they actively exchange with the main grid, but they are not autonomous. By contrast, the biogas and smart systems can meet demand with their own supply. Resiliency is the measure of performance during an extreme weather year. Specifically, it is the extra energy imported from the grid. Biogas and smart grid have better resiliency due to self-consumption. To assess costs, we used 2015 prices. As expected, every new system will cost more than the reference case. We also see that the cost of smart grid and power-to-gas systems are dominated by electric battery. To test the competitiveness over time, we performed the same calculations with updated prices for 2020. Here we observe the reduction of cost due to cheaper electric storage and an increase in cost due to more expensive electricity tariffs. Environmental impact is based on life cycle assessment studies. It includes embodied operational and end-of-life emissions. Here, the emissions are averaged over a lifetime of 20 years. Methane burning contributes the most in biogas system, while the national energy mix dominates the emissions in the power-to-gas, electric, and reference systems. To assess user satisfaction, we quantified the opposite, user dissatisfaction. It is a composite of how well a system meets 6 different measures. The first 2 measures were defined separately for each system at the design step. The remaining 4 originate from the user survey. Now we obtained the assessment of each individual criterion, we rank the systems and select the best one. With equal weights and 2015 prices, we see that the biogas and smart grid systems are the best choice for this neighborhood. However, when we adjust weights, we observe a change in ranking. This illustrates the importance of user feedback. In this case study, the biogas and smart grid systems consistently outperformed the other two designs. Yet, by changing weights, the best system also changes. Applying PACE to the Dutch neighborhood, we found that the biogas and smart grid systems are the most likely to meet user preferences. The choice between the two systems strongly depends on user feedback. The values and conditions dictate possible system designs and final ranking of the systems. That is why another country would have its own set of systems. In summary, decentralized energy systems are relatively fast and low-risk solutions for local energy transitions. They also allow to explore a variety of technologies. With PACE, we can navigate the solutions that will be socially acceptable and fulfill the technical needs. The energy transition is not a fixed predestined pathway, as local conditions and values are diverse. The Dutch case study shows the practical feasibility of PACE to find the optimal transition pathway that matches the local context, so that many nice transitions may flourish.